Have you ever wondered how messages travel so seamlessly across different networks in our hyperconnected world? In the realm of computer networking, bridging plays a pivotal role. Imagine a bustling city where numerous roads connect various neighborhoods. Similarly, in the digital world, bridging connects multiple local area networks, or LANs, to forge a larger unified network. This process is akin to building digital bridges that allow data to flow smoothly from one point to another. Bridges operate at the data link layer, which is layer 2 of the OSI, or Open Systems Interconnection model. Here they perform a critical function by directing data frames between separate networks. They make these decisions based on MAC addresses, which are unique identifiers assigned to devices within a network. By understanding where each device is located on the network, bridges ensure that data packets find the most efficient route to their destination, enhancing the flow of communication. So, bridging not only connects different network segments but also ensures that communication remains continuous and efficient. Imagine a city with numerous islands connected by several bridges. Each bridge has a specific role. In the world of computer networks, bridges serve a similar purpose. They connect different segments of a network, much like bridges connect islands, facilitating smooth and efficient communication across the entire network. Now, let's dive into how bridges operate at a technical level. Think of a bridge in a network as a smart mail sorting office. As data frames arrive, the bridge examines each one, particularly focusing on the media access control or MAC addresses. These addresses are unique identifiers for devices on a network, akin to the address on an envelope. When a data frame arrives, the bridge checks if the destination MAC address is on the same network segment as the source. If it is, the bridge, realizing that the data frame is already where it needs to be, does not forward it further. This is much like a letter that arrives in a sorting office already at its correct destination. There's no need to send it out for delivery again. However, if the destination MAC address is on a different segment, the scenario changes. The bridge then forwards the data frame to the appropriate segment. This is similar to how a sorting office sends letters out to different areas based on the address written on them. The bridge ensures that the data frame reaches the segment where the recipient device resides. Bridges are constantly learning and updating their knowledge. As they handle data frames, they learn where different devices are located based on their MAC addresses. This information is stored in what we call a forwarding table, a crucial element that helps the bridge make smart forwarding decisions quickly and efficiently. This process is essential for maintaining the flow of data across a network. It minimizes congestion and ensures that each part of the network can communicate effectively with the others without unnecessary data travel. Just as a well-organized mailroom ensures each letter reaches its destination, a network bridge ensures data packets find their right path across network segments. Every device on a network has a unique identifier, much like a fingerprint. This identifier is known as the MAC, or Media Access Control Address. It's a critical component in the orchestration of network traffic, particularly when it comes to the role of bridges in a network. Let's dive into how bridges handle these MAC addresses. Imagine a bridge as a keen observer at a busy intersection, watching the flow of traffic and noting down the license plates of every vehicle that passes by. In the digital world, bridges do something quite similar. They inspect the source MAC addresses of all incoming data frames. This is not just a passive observation. Bridges actively learn from this data. When a data frame arrives at a bridge, the device doesn't just forward this frame blindly. First, it checks its forwarding table, a dynamic ledger that keeps a record of which MAC addresses have been detected on which network segment. If it's a new address, the bridge adds this MAC address along with its corresponding port to the table. This process ensures that the bridge knows exactly where to send the data next time, streamlining the communication within the network. This dynamic learning is pivotal. Without it, a bridge would be akin to a mailroom that doesn't know which department sits where, causing delays as every piece of mail would need to be checked and queried. But with the MAC addresses learned and stored, the bridge efficiently routes the data to its correct destination, much like a well-organized mailroom dispatching letters swiftly to known locations. Furthermore, this learning capability of bridges isn't just about efficiency, it's also about network scalability. As more devices join the network, the bridge's ability to learn and remember new MAC addresses ensures that the network can expand without losing performance. Through learning and remembering MAC addresses, bridges grow smarter over time, optimizing the network's flow of data. What happens when a bridge encounters an unknown destination? Let's delve into the fascinating decision-making process that occurs within a network bridge when it comes across a data frame with a destination MAC address that isn't recognized. Imagine a bridge as a sort of intelligent gatekeeper of network traffic. Its primary role is to determine whether a data frame should be forwarded or restricted, based on the destination MAC address. Each frame that traverses the network carries this address, which acts as a specific identifier for the receiving device. When a frame arrives at the bridge, the first step is to check the destination MAC address against the bridge's forwarding table. This table is like the bridge's memory of where devices are located on the network. It contains a list of known MAC addresses and their corresponding segments. Now, suppose the destination MAC address of the frame isn't found in this table. What happens next is crucial for ensuring that the frame reaches its potential destination. The bridge doesn't just drop the frame. Instead, it takes a proactive approach by flooding the frame. This means the frame is sent out through all of the bridge's ports, except the one from which it was received. This flooding process casts a wide net, reaching out to all segments of the network. By flooding the frame, the bridge ensures that the data reaches every part of the network. This allows the intended receiving device, if present, to pick up the data. Once the device responds, the bridge can then learn and record the new MAC address in its forwarding table. This learning mechanism is vital as it helps the bridge make more informed decisions in the future, reducing the need to flood the network repeatedly. This method of dealing with unknown destinations is a fundamental aspect of how bridges maintain efficient and effective network communication. It ensures that even if a destination is initially unknown, there is a systematic approach to discovering and learning about new devices on the network. This method guarantees that no device is left out of the communication loop, enhancing network connectivity. Ever been stuck in a traffic loop? It's frustrating and unproductive, isn't it? In the world of computer networking, a similar situation can occur called a network loop. This happens when data frames circulate endlessly across network segments, causing possible congestion or even network crashes. To prevent such chaos, we have what's known as spanning tree protocols, like IEEE 802.1d. Spanning tree protocols are essential tools in the toolbox of network engineers to ensure that bridges do not create loops when connecting multiple network segments. Picture this. Each bridge in a network has the potential to send data frames to other bridges, which in turn might send them back to the original bridge, creating a loop. Without a way to manage these paths, the network could quickly become a tangled mess. This is where the spanning tree protocol comes into play. It intelligently disables redundant paths that could potentially form loops. By doing so, it ensures that there is always only one active path between any two network segments. This not only prevents the network from looping, but also optimizes the flow of data across the entire network. The protocol continuously monitors the network for changes, such as adding or removing bridges, and recalculates the best paths dynamically. It's a bit like having an air traffic controller who constantly updates flight paths to ensure that planes fly safely without colliding. By managing network paths intelligently, bridges help maintain a smooth and efficient network flow, much like traffic officers manage road systems. Not all bridges are built the same in the world of networks. Today, let's delve into the distinctions between transparent bridging and managed bridging, two pivotal techniques that shape how data travels across networks. Starting with transparent bridging, imagine it as the discreet yet efficient worker. It operates silently in the background of Ethernet networks. This type of bridging doesn't require any manual configuration from network administrators. It automatically learns the MAC addresses of devices on the network by examining the source addresses of incoming frames. The bridge then uses this information to update its forwarding table, ensuring data packets find the most efficient route to their destination. The beauty of transparent bridging lies in its simplicity and its ability to seamlessly connect devices without any fuss. On the other side of the spectrum, we have managed bridging. This method offers a hands-on approach, allowing network administrators to exert more control over the network. Through managed bridging, administrators can set specific policies, prioritize traffic, and segment the network to boost security and performance. It's like having a conductor for your network traffic, directing where and how data should flow. Managed bridging is particularly useful in complex network environments where tailored traffic management is essential to maintain optimal performance and security. Both bridging types serve crucial roles. Transparent bridging offers ease and simplicity, making it ideal for standard network setups. In contrast, managed bridging provides precision and control, catering to networks requiring detailed traffic management and enhanced security measures. Depending on the network's needs, administrators choose between automatic ease and controlled precision. Bridging is the unseen hero in the story of network connectivity. Let's take a moment to recap the pivotal role of bridges in computer networks. Operating at the data link layer, bridges serve as critical junctions that connect separate network segments or LANs into a unified network landscape. At the core of their operation, bridges efficiently manage data traffic. They examine MAC addresses in incoming data frames, deciding whether to forward or retain these frames based on their destination. This selective forwarding is pivotal in optimizing network traffic and reducing unnecessary data transmission. Furthermore, bridges are not just passive conduits, they are smart operators. They learn the MAC addresses of devices on each network segment dynamically, updating their forwarding tables to streamline the communication process. By employing protocols like the spanning tree protocol, bridges also ensure there are no disruptive loops within the network topology. Transparent and managed bridging options provide flexibility, catering to different network needs, from simple unmanaged connectivity to complex controlled network environments. As we continue to connect more devices and networks, bridges play an essential role in keeping our digital world seamlessly interconnected.